Now let us move on to the another important part, that is the Lemfel ZV encoding. So why did we get this type of coding? This is due to the drawback of the Huffman coding. So what happened is it required the knowledge of the probabilistic model of the source Huffman code. The source statistics are often unknown in the Huffman code. It needs extra memory to store that and reduce real-time applications. So what the advantages we get using this type of coding is, one is it is adaptive, no need any prior probability information, and it is simpler to implement. So the source data symbol, it is passed into segments that are shortened sequences not encountered previously. That is, if the segment is shortest as possible, and you need to move from left to right always. So we will consider this one example to understand the coding. In the step 1 initial code book, we will write has 0 and 1. This is, you have to write in every one. Starting, you need to start always with a 0 and 1. So while starting with this, we will update this book as what the first one, we will pair it up 0 0 and we will add it to here. Next, step 2. In the step 2, what is the next 2? That is 0 and 1. So I will add 0 and 1. In the step 3, I cannot add the 0 and 1 again because already the 0 and 1 has already been repeated here. So I need to add one more bit. It becomes 0, 1, 1. So next, 1, 0. 1, 0 is not repeated. You can use 1, 0. Next, 0, 1. You cannot use 0, 1. It's already been repeated here. So I'll make it as 0, 1, 0. Next 1, 0. Again 1, 0 is repeated. So I'll make it as 100. And next 1, 0. You can't. So it becomes 1, not 1. So this is how we do this type of coding. So after this, encode the parse phrase by the prefix and the last bit. So here this is what we had got using the subsequence that we have designed. Now numerical representation of this you need to write. So basically I am coding it. How am I coding? For the 0, I am writing it as 1. For the 1 I am writing it as 2. For the 0.1 I am writing it as 4, and for 1, 0 I am writing it as 6. I will divide the bits as prefix and the last bit. So last bit, here it is 0, so it is 1. Here it is 1, it is 2. As I said, for the 1 it is 2, for 0, 1, 0, 1, 0, 1, and for the 1 it is 2. Now come to the prefix. So prefix here it is what? 0. So this 0 becomes 1. Now 0, 1. It is 0, 1, it is 4. It is 1, it is 2. For the 0, 1, I have coded to 4. Then for 1, 0, I have coded to 6. Then for 1, 0, I have coded to 6. So this is how you will write the numerical representation of this. Now binary encoding blocks. So here what you have to do is encoding. Encoding is happening here. So 1, as I said, it is encoded as 0. It gets encoded by, for the 2 it is 1, for the 2 it is 1, for 1 0. Similarly, now for the 1 you write it as 0 0 1, for 1 it is 0 0 1, for 4 what it is actually 100. Next for the 2 you will have to write it in terms of 8421. In that format you need to decode them, that is 8421. So for the 4, how you can write it is 100. For 2 it is 10, 0, 10. For 4 it is 100. For 6 how it is 110. That is how you write the binary encoding box of the prefix. Next, you need to know the fixed size of block. The fixed block size is 12 bits is used. So in the code book it should be 2 power 10, that is 4096 entries to be there in the code book. So this was all about that type of coding. If they ask you to explain it, you have to write it clearly. Next is discrete memoryless channels. Here is the static model of communication. This is a input is the random variable x with a finite alphabet. Output is a random variable y with a finite alphabet. Output is y. It is a noisy version of the x. So you can say this is memoryless because the current output depends only on the current input. There is no memory to store. So let us consider an input alphabet as x. x0 to xj minus 1, output alphabet as y, that is y0 to yk minus 1. Here each input symbol can produce different output symbol with a certain probabilities. So this is how you can represent the discrete memoryless channel as input. You will send it to a probability, and for none you will get an output. You can observe it: input x with sample x, output y is sample y. This is a simple graphical representation of the discrete memoryless channel. Probabilities is it should lie between 0 to 1, and the summation of all the probabilities should be equal to 1. Transition probability, this is the formula, and channel matrix. So here transition matrix is important. So this is how it is written as y0 by x0, y1 by x1, and yk minus 1. So this is each row what we are having. This is having a fixed input. So you can observe here it is x0, x0, x0. So input is fixed in each row. And then in the each column, output is fixed, y0, y0, y0. So input is fixed in row and output is fixed in the column. And each row sum should be equal to 1. If you add all this summation of the each row should be equal to 1. So it is also called as a stochastic matrix. Next is joint probability of the input and output. Let us consider here we are having xj and yk. So here p of y is equal to yk and x is equal to xj. So into p of x is equal to xj by the probability theory. Now the marginal probability of the output. Here the marginal probability is p of yk is equal to summation of j is equal to 0 to j minus 1 and PYK into P of xj. So summing up the joint probability over the input symbols. Next is the binary symmetric channel. So this is a special case in the discrete memoryless channel where the input size is 2 and output size is also 2 in the above case. So then what happens? My x and y will be only 0, 1 and 0, 1. Probability will be what? 1 by 0. It is 0 by 1. It's equal to P. 0, 0 and 1, 1 will be 1 minus P. Probability of 0 being received as 1 is same as the probability of 1 being received as 0. Now the channel transition matrix, that is stochastic matrix, is written as 1 minus P 1 minus P. So as I said, if we add this 1 minus P and P, we are getting 1. So row sum is 1. Row is having an input symbol and column is having the output symbol. Now, transition probability diagram. This is another one important thing you need to know. Here, how do you write is you need to write the input in the left and output in the right hand. So x0 is our first input and x1 has 0 and 1. Output is y0 and y1. What probability we are having is here 1 by p, x0. And from the x1 it is p. From x0 it is p and from the x1 it is 1 minus p. So hence you can say it is memoryless and the symmetric. Next is conditional probability. You know that from the previous years you have been learning about this. This is the conditional probability formula. Now conditional entropy. So this is a equation for the conditional entropy. It is an average uncertainty remaining about the input x after y is output is observed. So that is what called as conditional probability entropy. So based on that, on expanding this, you can write it also has this type of equation. So before observing the output, it is uncertainty is h of x. After observing, it is h of x by y. Next comes the most important topic of this module, that is the mutual information. So this is a very important part. It is a reduction in the uncertainty about the channel input x obtained by observing the channel output y. It is, you have to note, it is the reduction in the uncertainty. You need to reduce. That is what happens in a mutual information. How much of information y gets about x? This is what, how reliable the channel is can be decided. So if the larger the mutual information, then better will be the channel. So for a perfect channel, the h of x by y, it should be equal to 0. Then the information transmitted will be maximum. If it is a noisy channel, then xy will be larger and hence the information will be minimum. Now, conditional entropy. We know we got this formula from the previously. So h of x by y can be written like this because this summation of p1 by log p is equal to h, and hence by using the joint probability we know this equation, and substituting it for this part we can write that as p of xj comma yk log of 1 by pxj by yk. So here h of x is what? Entropy by itself of input. H of xyk means uncertainty after the output is known. So you can write I of x comma xy is equal to h of x minus h of x by y. I of yx is to h of y minus h of y by x. So this is how you derive the mutual information. Next, properties. The first property of the mutual information is it is symmetric in nature. That is, I of xy is equal to I of yx. Information of x gives about y is equal to information y that gives about. So by the definition of entropy, we know this formula. So for this formula, P of xj using the total probability, we can write this formula by substituting the equation 2, means substituting this P of xj in this place, we get h of x as summation of j is equal to 0 to j minus 1 and this equation. So as I said previously, with the joint probability, we can write it as like this. So finally, we get the equation. By using the base law, you can write this P of xj by yk by p of xj has p of yk by xj divided by yk. So on replacing that and changing the summation order, you get this. So finally, hence the symmetry is proved. Next property is the non-negativity always. That is, I of x is that is to y is always negative. Is always non-negative. I'm sorry. Then I of xy is what it is, j is equal to 0 to j minus 1, k is equal to 0 to k minus 1, and this formula. For this, we know this can be written as p of xj into p of ik if y, x1, and y are independent. So the fundamental inequality of the log is the sum is always greater than 0. So we cannot lose the information and average by observing the output of the channel. So what happens if that is 0? Mutual information is 0 if and only if the input and the output are statistically independent, then p of xj comma yk is equal to p of xj into p of yk. Next property is the expansion of mutual information. So mutual information is related to a joint entropy of the channel input and the channel output by this formula. I of x that of y is equal to h of x plus h of y minus h of x comma y. Here joint entropy can be written like this with two summations and this formula. We rewrite this. We rewrite this using the log function, that is p of 1 by p of p of 1 by p of xj comma yk, that can be separated and written like this. Now I will send this summation to the left side, and I'll write it as log 2 of this p of xj yk divided by p of xj into yk, which is equal to minus I of x that to y. So the second term is simplified using this formula, and this formula, that is k user limit and j limit. So hence it becomes h of x plus h of y. So h of x comma y is equal to h of x plus h of y minus x of x that of y. On replacing this to left and taking this to right, we get the obtained formula. Now, for that, we can take an example as we had read before. For a channels shown, write the channel matrix. So this is a channel that's been given here. It is 0.8 here, 0.6, 0.4, and 0.5. x1, x2, x3, these are the inputs, and y1, y2, y3 are the outputs. So how y1 by x1 is given? y1 by x1 is 0.8. y1 by x2, it is what, 0.6. y2 by x3 is 0.4, and y3 by x3 is 0.5. So write down the probabilities of them. Then what is y2 by x1, what is this order? Once it is going 0.8 means obviously here it should be 0.2. Similarly, find out y3 by x2, that is y3 by x2. What is that will be? That will be 0.4. Next, y1 by x3. This, what will be this? It will be 0.1. Now, write down the transition matrix. That is what, as I said, input should be same in each row and output should be same in each column. Based on that, write down this matrix, and from the values that we have obtained from here and from here, substitute those values, and here you can observe that each row adds up to 1. So 0.2, 0.8 is 1, 0.6, 0.4 is 1, 0.1, 0.4, 0.5 is 1. Next is the channel capacity. Here, before going to that, we can move on to some of the problems that has been asked. Okay, that is being asked. Yeah. So this is what I explained now, and this is one more. The in the given binary symmetric channel, binary symmetric means it is having input of 0, 1 only. The probability is given as 0.7. So you can say 0 by 0 is what is equal to 1 is to 1. So hence it is 0.7. So the channel matrix will be equal to what? 1 is 0.7, 0.3, 0.3, 0.7. This is the channel matrix. Similarly, here for a channel matrix that is given, you need to find the missing entries and draw the corresponding channel diagram. We know that in each of that, each row should correspond equal, some summation of each row should be equal to 1. So obviously, let's see what the values we should be getting there. So here it is 1 minus 0.8 minus 0.2. The first value is 0, second value is 0.2, third value is 0.5. And from that you need to draw. So 0.8 is going here, 0.2, 0.2, 0.6, 0.2. So you can observe here this is equal to 1, this is equal to 1, and this is equal to 1. So next comes for the joint probability, you need to find these values where the joint probability matrix is given like this. So this is also an important question. It's been asked. You need to find these values. So here we know that the sum of all the elements of the row is equal to 1. So it gives the corresponding input to the input probability correspondingly, and that of the column gives the output probability. So let us observe for the input, p of x is equal to 0 0.3, 0 0.2, 0 0.0, 0 0.3, 0 0.2. And for the output, it is, you can observe once if you substitute here as 0.3 that is being given, you get the row as 1. So similarly, you find out for each one what are the missing things there. And finally, we have the entropy equation. Apply to the entropy equation. You get the entropy of 1 pxi, and for the pyj, you get 2 h of x, h of y. Now, what you need to find next one is h of x comma y. For that, we know the formula previously we had learned. Apply this formula, we get h of x comma y. Then h of x by y. Using this formula, you need to find it, and do not p of xy is equal to p of x comma p of y. Divide each row by the joint probability input probabilities, that is divide all the elements for the first row px1 and the second row by px2. So you get the channel matrix y by x as like this. So then find the entropy of that. So finally you reverse it, h of x by y. So same thing, do it again for this row and you'll be getting this value. Now same given channel matrix is given, you need to also the input matrix is also given. You need to find the same thing. As I said, this is an important question where you have to find all these values. It will be given in the exam. Don't skip this part. So here h of x, h of y, same thing. If you solve, you will be getting this as answers. To check and verify. And mutual information is given as 0 0.8, 0 0.2, 0 0.3, 0 0.7. we have a mutual information formula has like this. For that, you substitute that. Here you can directly obtain from the channel diagram. So also from the joint probability matrix using this formula you can write, and P of x comma y can be given, and find the entropy of h y and h of y by x. So similarly, you can go through these problems. These problems are quite important and good. So next we will move on to the another topic, that is the channel capacity. Here we know that entropy is nothing but it is about the uncertainty. Mutual information, it is about the information that is transferred from input to output. So Shannon said that maximum reliable information in a channel can carry is called as a channel capacity. How much maximum information that it can be carried. From the discrete memoryless channel, that is DMC, input of a symbol is xj from j to j minus 1. Output symbol is yj from y to k minus 1. Transition probability is given by P of yk by xj, and mutual information is given by I of x is that to y is given by this formula. We know this can be written as uh, replaced by this formula, and finally we can replace P of yk and P of xjyk. Finally, the channel capacity definition is given as the C, it is represented by C, it is given as maximum probability of xj in the mutual information, that is bits per channel used. Here this should be greater than 0, and if j is equal, it should lie between the j is equal to 0 to j minus 1, then summation is 1. So you can also define it as maximum information of a channel that can transmit in one use, assuming the best possible input in the distribution. The channel capacity is an intrinsic property of the channel. So in that mainly we are focusing about the BSC, that is the binary symmetric channel. This is an important question, and this had been asked in December Jan 2025 paper. Here what consider as an input. Input symbol as x naught, output symbol as y naught. What is the error probability? It is P. Transition probability, it is given by the P and P1 minus P, and the entropy of both of them is equal to 1 by 2. In the binary symmetric channel, the input distribution also maximizes the mutual information, so that both of them are equal to 1 by 2. Now channel capacity formula, you need to know the formula. C is equal to, substitute it, 1 plus P log 2P plus 1 minus P into P log 2P. Same, you apply that formula here, and by the binary entropy function, you can write entropy as by simplifying this. And finally, this is the important equation that you have to know, channel capacity formula. It is given by C is equal to 1 by H of P. In case if P is 0, what will be in what happens is it becomes a noise free, because H of 0 is 0. C is equal to 1 minus 0, and C will become 1. So you can say here transmitted bits are received correctly here. This is the best case. Next, see case 2, here P is equal to 1 by 2. This is completely a noisy channel. H of 1 by 2 is 1, so C is equal to 1 by 1 minus 1. So here no information will be conveyed. So this is the worst case. Next, the general behavior. Usually what happens is capacity curve is convex always. Consider P is equal to 1 by 2. Then the as the noise increases, the capacity goes on decreasing. If the capacity increases, if the noise decreases, then the capacity increases. You can observe here, if this is the transition probability and this is the capacity, you can observe it is maximum when it is 0, and it is minimum when it is 0.5. Then why do we need channel coding? Because it adds a controlled redundancy and it detects and corrects the error. Transmission is reliable even despite of the noise. Then noise causes what? It causes any bit errors. So like P is equal to 10 power minus 1, only 9 out of the 10 bits are correct. So this problem is without the channel coding. So you can observe only 9 is correct out of the transmitted bits. So there are many errors in the bits. So to overcome this problem, we use the channel coding so that it adds a controlled redundancy, it will correct and detect, and transmission will be reliable. Now, so that arises to the channel coding theorem. This is also important. This was asked in the model question paper. Here, discrete memoryless source. Here, firstly, from the it gives the input source to the channel coder. This is called a transmitter, and here it gets encoded and sent to the discrete memoryless channel through the DMC along with the noise. And finally, we are having the channel decoder, and where the receiver receives the destination information. So consider we will take k source bit, it is mapped to the encoded bit where n is always greater than k. We are having redundant bits, that is n minus k, so our code rate will be k by n. This is also an important formula that you have to know while solving the problem. Rate decreases, then the redundancy increases, better error protection. So this is the Shannon's second theorem. We will see what happens in the source side. We are having source entropy h of s. It is emitted in the symbol in Ts seconds. In the source information, it is given by h of s by capital Ts. In the channel side, we are having the channel capacity. Channel uses every T seconds, and channel capacity per unit is given by C by Ts bits per second. Now comes the channel coding theorem. So first property it is achievable, as h of s by Ts is less than or equal to C by Ts. This is, you can say, achievable task. Coding scheme and probability of the error is 0 and block length can be infinite. So this is a critical rate, you can see. Next, if it is converse, converse is nothing but this h of s by ts is greater than c by ts, then the communication becomes impossible. Error probability cannot be made small. Therefore, you can transmit information reliable if and only if your rate is less than or equal to channel capacity. Then what will be the limitations of this? It does not tell us how to design the code, and it is asymptotic results, so there is no finite length. This is the drawback. Next application of this theorem is source entropies h of s is 1 bit per second. Source emits every ts second, so our rate is given by 1 by ts. Bit symmetric capacity, binary symmetric capacity channel with the capacity is given by C is equal to 1 minus h of p. Channel uses once every tc. So substituting that 1 by ts here, 1 by ts is equal to c by tc. So replace it. Tc by ts is less than or equal to c. R is given by k by n, that is equal to tc by ts. So you can say R is less than or equal to c. Last concept, that is the information capacity law. This has been asked in the model question paper and in the syllabus. We are having only the statement. Statement states that the information capacity of a continuous channel of the bandwidth V hertz perturbed by the AWGN of the power spectral density N naught and is limited in the bandwidth of P1. It is given by the formula C is equal to B log 2 of 1 plus P divided by N naught P of bits per second, where our P is the average power transmitted. So this completes the module 3 of the digital communication subject. I hope everything is clear for you, and do study well and do well in your exams. Thank you for watching. Do like and share and subscribe to Exam Ignite. See you in the next video.